Hello, students, and welcome back. Let me start with a fascinating thought. Have you ever wondered why the air you breathe is made of water molecules and carbon dioxide, not just random atoms of hydrogen, oxygen, or carbon floating around? The truth is, atoms almost never like to stay alone. They prefer to form groups or molecules because in doing so they achieve stability. This tendency to unite and stay bound is what we call chemical bonding. By definition, a chemical bond is the attractive force that holds atoms or ions together in a molecule or a crystal. The real driving factor here is stability. Most atoms are restless unless they reach an electron configuration like that of the noble gases, the so called octet rule, where they have 8 electrons in their outer shell. Think of it like chairs around a dining table. When the table is full, it feels complete. That's exactly why sodium bonds with chlorine or why oxygen pairs up with hydrogen to reach that comforting, stable arrangement. The very table salt you sprinkle on your food or the water you drink is a product of this quest for stability through bonding. Now, why exactly do atoms do this? The secret lies in energy. Atoms form bonds because it allows them to settle into a state of lower energy, which automatically makes them more stable. Just as a ball naturally rolls down a slope to rest at the lowest point, atoms do roll down into lower energy states by bonding. Here's a beautiful chemical example. When hydrogen gas reacts with chlorine gas, the two combine to form hydrogen chloride gas. We write this reaction as H2 gas plus Cl2 gas gives to HCl gas, and in this process, a lot of energy is released. The message is clear: bond formation is always accompanied by the release of energy, while breaking a bond requires the absorption of energy. This principle, in fact, is rooted in the law of conservation of energy. Energy is never lost, it only changes form, stored inside the compounds we see and use every day. So, how do atoms bond? Broadly, chemistry recognizes three main ways: ionic bonds, covalent bonds, and coordinate bonds. An ionic bond forms when atoms transfer electrons, typically a metal giving away electrons to a nonmetal. Sodium and chlorine forming table salt, NaCl, is the most famous example. A covalent bond, on the other hand, is all about sharing electrons. Nonmetals like hydrogen and oxygen share pairs of electrons to form molecules such as water. Finally, we have the coordinate bond, a slightly special case where one atom donates both electrons to form a bond, as seen in the ammonium ion. These three bonding styles explain why substances look and behave so differently. Salt is a hard, crystalline solid, while covalent compounds like carbon dioxide exist as gases. Isn't it amazing how the invisible dance of electrons shapes the entire material world around us? Let's dive deeper into the first type, the ionic bond. By definition, this is the electrostatic force of attraction between positively charged ions, called cations, and negatively charged ions, called anions. Take sodium with its electron arrangement 2, 8, 1. Sodium happily loses that one electron to become sodium ion. Chlorine, which has 2, 8, 7, readily accepts that electron to complete its octet and becomes chlorine ion. These oppositely charged ions are then strongly attracted, forming sodium chloride. We can write it step by step as sodium plus chlorine gives sodium ion plus chloride ion, which together form sodium chloride. Ionic compounds like this usually have high melting points because so much energy is needed to break those strong electrostatic forces. And here's a fun fact: they conduct electricity, but only when molten or dissolved in water, because that's when their ions are free to move. Now let's turn to covalent bonding. Instead of transferring, atoms here share electrons to achieve stability. A covalent bond is defined as the mutual sharing of one or more pairs of electrons between atoms. For example, two hydrogen atoms share one pair to form a single bond, written as H-H. Oxygen atoms share two pairs, forming a double bond, O, while nitrogen atoms share three pairs, forming a triple bond, N. These shared electrons keep the atoms tightly linked. But because there are no charged ions involved, covalent compounds behave differently. They often have low melting points, many are liquids or gases at room temperature, and they usually don't conduct electricity. Think of carbon dioxide in your fizzy drink or methane gas used for cooking. Both are classic examples of covalent bonding at work. There's also a special kind of covalent bond called the coordinate bond or dative bond. In this case, one atom contributes both electrons to form the bond. A common textbook example is the ammonium ion. Here, the nitrogen atom, with its lone pair of electrons, donates that entire pair to bond with a hydrogen ion. To represent this, we use an arrow showing nitrogen donating its electron pair towards hydrogen, written as an arrow H. Such bonds often appear in complex ions and coordination compounds. What's remarkable is how versatile electron sharing can be. Whether shared equally, unequally, or donated completely, electrons always find a way to keep atoms united. So, let's quickly connect everything we've learned. Atoms bond because they want stability, often through the octet rule. Bonding also lowers their energy, making them more secure. We saw three major types: ionic bonds formed by transfer of electrons, covalent bonds formed by sharing, and coordinate bonds where one atom donates both electrons. We also discovered that these bonds explain why materials around us are so different: crystalline salts, gaseous molecules, even the air we breathe. So, next time you stir sugar into your tea or strike a matchstick, remember the chemistry of bonding is behind it all. Understanding chemical bonding is like discovering the secret glue of the universe, the invisible force that holds matter together. I hope this session gave you clarity and curiosity, because chemistry is not just about equations, it's the science that explains why everything in your world exists the way it does. See you in the next class, where we'll uncover even more fascinating secrets of chemistry.